Hello and welcome to our Physics 1405 Zoom. Can I get a verification that you can hear me and see our whiteboard for our possible discussions here?
Yes, I can see it.
Yes, I can hear you
Okay.
and see it.
All right, great. Just an announcement, moving forward, if you're asking questions and you would like participation credit, please also type your question in the chat so we have a record that remains after the meeting is over. The people who are here now get precedence, so if anybody has a question that they would like to ask to get the meeting going, feel free to get started. All right, I'm seeing two of you and you're muted. Does anybody have a question? If not, we will refer there are a question or two in our discussion forum that we can discuss.
I do. I started to type it out. Do you want me to
Okay.
just say it?
Yeah, go ahead and just say it for now, and then just make sure to finish up the comment and make sure it gets
Okay.
into the record for the meeting.
Okay. I feel kind of silly asking this, but to be honest, I'm just getting back in town, so I'm reading everything and I watched the video. We are not doing the actual lab like with an action figure, correct? We're using the stuff in the Excel spreadsheet, right?
Yeah.
To calculate our answers. Okay.
So the action figure, that's the physical lab that students who are doing an in-classroom lab do, and then yeah, they provide you some data to use.
Got it. Okay. Just wanted to be sure. Thank you.
One of the questions that the students are commenting on is that the numbers tend to change. So that file is a dynamic file that's meant to present each of you with slightly different data representing the natural variation you would get in the lab. So you need to open that file and use that data, and then your final results, you need to print that to PDF or something to submit it. If you open and shut the file a bunch, you will discover that it changes on you. So that's something that the students need to be aware of. Just go through the lab with the data that you have and then make sure to print your final results to PDF, and
Okay.
don't leave the lab and come back a lot because you will discover that it is dynamic data.
Got it. Okay, got it.
Any other thoughts? I believe that the other question is about the energy, and I do want to discuss that a little bit. So okay. I do not remember the exact points, so give me a moment to pull open the lab, what they do, and we will actually do a little bit of diagramming here. What kind of pencil do I have at the moment? All right. So our hypothetical situation is that we're releasing our character from a certain height, h. And they want us to discuss the kinetic energy at various points. And there's a little table that you guys need to fill out. Have you guys gone over the concept generally of conservation of energy?
Yes.
Okay, so you are familiar with that. The idea is that energy cannot be created or destroyed. It's just changed from one type to another. So quantitatively, if I said, you are standing on the balcony in the back of the library, getting ready to release your action figure over the edge, how much energy does it have? What would you say?
None at that point.
Well, you've taken up the stairs a certain height, and that's
I thought you meant just holding it in your hand before you.
Yeah. So we are counting that, and this is potential energy. So that's one thing, is that our potential energy is counted from an arbitrary point. And so in this experiment, the arbitrary point is going to be the lowest point that it goes to. And hypothetically, we're trying to make that as close to the ground as possible. So let's just pretend that your figure is going to get right down all the way to the ground and just barely not touch but meet that point. And if it does, and you're standing up above, we've already discussed that it doesn't have a lot of energy, but what energy it does have we're going to label these. You guys can see my whiteboard here, right?
Yes.
Okay, so these are the three types of energy that it could possibly have. And we're going to say this is a closed system. We're going to neglect air resistance or anything that might be taking small amounts of energy out. We're going to say mathematically, it's basically a closed system. So we can tally up our energy. We know it's in one of these three buckets. So when we start off at the top, kinetic energy, you have it if it's moving at all. So if you're just holding it, about to release it at the top, there's no kinetic energy. Spring potential energy, you have it if your stretchy springs, which in this case are rubber bands, are stretching. All the energy that it takes to physically stretch it stores some in the rubber bands. So at the very beginning, we have none. So all of your energy is in this potential energy. It's 100%. And quantitatively, if you wanted to measure that, which I do believe you might have a question that says hypothetically at this height, how much do you have? The number is m times g times h. So you could calculate that. And since we know, I'm putting an equal sign there, since we know that this is how much energy we have in our system, and we're going to have 100% of this energy in one of these three buckets all the time, or a combination of the buckets. We know that the total quantity of energy in our system numerically is mgh. So if you have a question in your lab that says quantitatively how much energy do you have, it's that. Even if it's at some later point where some of the energy has migrated to somewhere else, the number we have is still going to be the total added up will be that amount. Okay, so what's our first point later? Let's put another point down here. And I believe it can. Well, your question in your lab gives you 5 points A, B, C, D, E, I believe, and I don't remember exactly what they are. But we are.
Go ahead. Sorry.
Go ahead. If you're able to read it, go ahead and read it.
Yes. Point A says the instant before the figure drops, it is at rest and the spring is not stretched.
All right. So that's the same as the one that we did. Okay. What's the next one?
Point B says an instant when the figure is falling. It is lower than its original position. Okay. Yeah.
Okay, great. So we'll just do B here too, since we know that we have the same ones as the lab. We won't use alternate numbering anymore. So if it's falling, how much energy does it have? It has some quantity in potential, right? So less than 100. And that means it's decreasing, right? We'll draw a little down arrow, so decreasing. So potential energy is directly related to height. So at all heights less than our full height, it's going to be getting smaller and smaller unless it's turned around and coming back up, right? So it's decreasing. What's happening to our kinetic energy?
Increasing.
It's increasing because it's getting faster, right? Kinetic energy is 1/2 mv squared, and our velocity is going up. And what's happening to our spring? Is there anything there yet?
I think yes, right? Because it's pulling on the rubber band.
Nothing that the rubber band is blowing in the wind, unless it actually says that it's starting to stretch or it has stretched. We're going to say that there's none in the spring. So this fact that the spring is there, it could start to collect energy, but it doesn't actually do that until it starts to stretch. So there's none there at the moment. Okay, what's the next point?
C says the very last instant for which the figure is falling, but the spring has not yet begun to stretch.
Okay, so what have we got going on there?
Still some potential energy.
And what's still happening to it? Is going up, going down, staying the same?
Down.
Yeah. So our potential energy continues to decrease. What's happening? Kinetic energy?
I think it's still increasing because it's still moving.
But we do know something about it because this is the last instant that before it starts to stretch. Well, what happens as the stretching happens? What happens to our kinetic energy?
As the stretching is slowing down.
Yeah, so that means that we are at a maximum here, meaning we're not well, we are about to decrease, but at this precise moment, we are neither increasing or decreasing. We've hit our peak as far as kinetic energy is concerned. And then as far as our spring potential energy, technically we still have 0 at this moment, but it's about to start loading into that.
Okay.
Wonderful. So our next point.
Okay, D says an instant when the figure is falling and the spring is stretching.
Okay, so what happens here? So potential energy, go ahead.
Yeah, I was just thinking it through. Because it's falling for an instant and the spring is stretching. I don't know.
Well, let's just look at our column. Potential energy is directly proportional to height. So what do we expect that to do? Even if the string is stretching, what is happening to the height?
It's decreasing.
It's still going down.
Yeah.
All right. So what's happening to our kinetic energy as the spring is stretching?
It's decreasing now.
Okay,
it's
so
maxed out.
Yep, now it's decreasing. So what's happening to our spring potential energy as the stretching is happening?
It's increasing.
Great. All right, perfect. So there's one more, right?
Yes. So E says the instant at which the figure has reached its lowest position and is momentarily motionless before rebounding.
Yep. Great. So let's put E all the way down there at the bottom. So if it says motionless, that implies velocity equals 0, right? So what do we know right away about our kinetic energy?
It should be 0.
Yep. And what's happening to our potential energy?
It's motionless, so I think it's stopped, right?
Yeah.
Yeah.
Well, the stopping is our kinetic. Our potential is directly related to our height. And the moment it gets to its maximum lowest position, we've defined that as H equals 0.
Yes.
So what are we going to call our potential energy then?
0.
0 or minimum. Like if you define your height slightly differently, like if you measure it from the ground and it doesn't quite get to the ground, you could squidge on that. But normally we're measuring this as the height it drops. And if we do that, then it's numerically 0 at that point. So what do we know if there's only 3 buckets to put our potential or whatever, our total energy, there's only 3 buckets in and we've just zeroed out 2 of them. What does that mean about the third one?
It has to be 100%.
Yep. So 100% or maximum. And technically it's not increasing anymore because the next moment after this is not going to be any greater, right? So this is a maximum. So maximums or minimums, we are not increasing or decreasing anymore.
Okay.
All right. Does that start to make sense to anyone?
Yes.
Great. You guys have had great questions, and you see how, this might be daunting if I said, tell me a story about where the energy is and where it's going. But if you understand each type of energy and how to measure it, then you can think through one step after another, and you guys know a lot more about this than you think you do. So good job. All right. That's as much as I see for the questions that were posted in the discussion forum. Has anybody else seen any questions posted, or is there any outstanding comments from the lab that are confusing?
I think those were the only questions. I can't think of any others right now.
Okay,
I can't either.
All right, great. I think that this should be pretty good. This table is the kind of the tricky thing about the lab, and I kind of love it because it's a good overview. Like after being able to think through something like this, you guys usually have a good grasp of conservation of energy, which is one of our big concepts for this lab. So I'm happy with that. Make sure any comments or contributions that you guys want credit for are listed in the chat, so I have those to record afterwards. we will go ahead and end this video and get it processing, and shortly it will be uploaded to the link and posted to the page.
Okay.
All
Thank you,
right.
Professor.
Thank you guys so much. It's great to see you.
Thank you.
Bye.
Bye.